So let's do some proportional integral PI controller design. So when studying steady state error, as you may recall from a couple chapters ago, we discovered that the more integrators in the loop transfer function, the better the steady state error. PI control includes an integrator compensator to be a proportional integrator controller. And the idea is that we include this integral compensator without significantly affecting the transient response that we had after our proportional design. So we do a proportional control design, and then we add an integral compensator to it, hopefully not affecting the transient response too much, at least not adversely affecting it. Sometimes you can get lucky and you'll positively impact the transient response when you add the integrator. Typically, the opposite is true, however. So we will sort of go through and learn this technique. It's one technique. There are others you can use to design a PI controller, but this is a root locus based technique, and it's fairly effective. It's probably my favorite for PI control. Great. And then then we'll learn how to do PID control built off of this, but we're going to stop and do a proportional lag controller to sort of show that side of things as well, the other class of controllers that are approximately like PID controllers, but they can be instantiated in those passive circuits. So here's the plan. Include an integrator, i.e. a pole at the origin, in the controller, and a nearby zero to counter the pole's slowing effects on the transient response. So whenever we just plop a pole in to our root locus, it's going to really, especially on the real axis, we're going to just throw the whole transient response off. The whole thing is going to change. The whole root locus shape will change. You could make something that was stable into something that's unstable, for instance. So just a lot of bad stuff happens when you just drop an integrator in. So we put in a nearby zero to try to counteract that effect. Okay, so why does the integrator affect the transient response? Adding a pole at the origin completely changes the root locus, and therefore the location of the close of the poles, and therefore the transient response. In order to mitigate this, we place a zero near the origin, so near that integrator, which nearly cancels the integrator's effect on the root locus. And to see why this happens, remember that the root locus, every location on the root locus must meet the angle criterion from lecture 5.1. So let us meditate on figure 6.3, in which a system is presented that initially contained 3 left half plane poles and no zeros. So let's look at this. So the idea is that originally we had 3 left half plane poles, and if we draw the root locus for that, and we're just ignoring these for the moment, we'd have no locus, locus on the real axis, no locus, locus. Great. We look and see there are 3 poles and no zeros, so there must be 3 zeros at infinity. 3 asymptotes, if you were to calculate them, they would be at pi over 3, pi, and then negative pi over 3. So it's going to be this angle, that angle, and this angle that the root locus goes to. If you just drop in a pole, so we'll include this pole now, the integrator at the origin, if we were to redraw the root locus, notice how significantly this changes things. So you'd have no locus, locus now up to here, no locus here, and then locus again, and then no locus out here. So completely different. We would have 4 asymptotes now, and we would go off the root locus would come off and go like this. And we would have a system that, if you increase the gain, would actually go unstable at a certain point. Big changes to how the transient response behaves. So we just dropped in the integrator, big things happen. But if we also include a nearby 0, okay, then the net angle contribution of this pole and 0 to locations on the root locus are essentially canceled. And we see that by saying, okay, the original angle criterion was that with these 3 poles, this, so theta 3, theta 4, and theta 5, had to sum up to pi, or 2 pi plus pi, or 4 pi plus pi, etc. So that's what 6.4 is telling you. So we had theta 3, theta 4, and theta 5, all pole angles. So they're all negative here. We had to add up to pi. Now, when we added in our theta 1, our integrator angle, that threw the whole thing off, right? So this criterion, when you included theta 1, completely changed where all of these locations would be. But if we also include a theta 2, it's a 0, so the angle contributes in an opposite way. Essentially, the theta 1 and theta 2, if they're approximately equal to each other, then they will cancel in effect. So the root locus will stay approximately where it is. So if you look at the root locus here now, then you have 0 root locus, and then you have locus between these two, the compensator pole and the compensator 0. No locus, locus, sort of like the original one, no locus, and then locus. You look at 3 zeros at infinity, the asymptotes go off in the same angles, and the same stuff occurs. So there's really not as much of a difference now. So now we've got this nice locus going similar to how it was before. There's a slight difference, of course, because we don't want to put the 0 on top of the pole, which would effectively cancel it out. But if it's just nearby, its effect in terms of steady-state error are equivalent, but the effects in terms of transient response are not. And what we're seeing here is there's actually a trade-off that we'll see when we do the example too. The trade-off is between affecting the transient response. So if they're very close together, the transient response is hardly affected at all compared to how it was before we added the compensator, the integral compensator. But if the more we move this 0 to the left, so we could just keep moving that 0, like out here, for instance, or if you keep getting too close to this pole, you're in danger of canceling it, and that changes the root locus again. But as long as you move it leftward, if you move it leftward more and more, it does affect where this location occurs. However, you get a system typically that's going to respond faster, or not respond faster, but the steady-state error will be compensated for faster. Okay, so we'll see how that works. We'll actually play with this in an example in just a moment. But that's approximately the idea of doing a PI controller. So we'll learn this design procedure, and then we'll just march through an example and do a design problem. So the following design procedure can guide us through this typically straightforward controller design. It's actually it's pretty much it's pretty straightforward, not too bad. Okay, so first design a proportional controller to meet the transient response requirements by choosing the gain K for the dominant closed loop poles to be P12, so whatever that location is to meet the transient response criterion. So if it's percent overshoot, or if it was the rise time or settling time, these are the transient response criteria that we would be designing for. So once you've got that met with just a proportional controller, then we want to also say this is a system that has some steady-state error beyond what we want. So say it's a finite steady-state error for a step response, and we would like to compensate that by adding an integrator that reduces the steady-state response, steady-state error to 0. So then we're going to include Cascade integral compensation and a real zero near, so that this just gives you a starting point. So say, let's take wherever this dominant closed loop pole pair is that's dominating the transient response, let's divide that by 10. This is just like an arbitrary choice. I mean, it's saying, okay, if you divide it by 10, you're going to affect the transient response very little. Gives you a place to start. If this works, then good. But oftentimes you start here and then you move that zero around. You always put the pole at the origin, so you don't really have any choices there. Put the pole at the origin. The zero, though, you can put kind of arbitrarily depending on how your performance comes out. So step 3 then is to tune the gain again such that the closed loop poles are desirable as possible. So like you messed up the transient response a little bit when you added in the integrator. So we go back and retune a little bit, which is usually not too bad. Usually you don't have to change too much. And then simulate the time responses and see if it meets specs. Tune, if the steady state compensation is too slow, which is often the case. When you use this real part of the poles, the over 10 rule, you get something that's pretty conservative, and it's a pretty slow compensation of the steady state error. So oftentimes you're going to want to move the zero leftward. Move the zero further leftward. You're going to screw up your transient response a little bit oftentimes, but you're often willing to give a little bit on that spec, as long as you can get that steady state error gone. And another way to think about this is you can say you do that, you move the zero leftward, it's slower, you slow down, or you speed up your steady state error compensation. Then you go back and you say, okay, what happens if I increase the gain now? And sometimes you can really actually recover a lot of that transient response that you lost, this transient response performance that you lost if you increase that gain. So at that point, it's a little bit of a trial and error situation. You can set up loops. I noticed that some of you in class were already doing that with the proportional gain to try to get a certain settling time or something like that by just putting it in a loop and evaluating the step response using step info. So yeah, that's a great way to do it. You can also do that. You can automate the process of searching for the gain, in this case, too, for the proportional integral controller. So that's the procedure. And once again, plans are useless, but planning is essential. So we start off with these guidelines and we just march through. We do our best, and some systems are harder to design PI controllers for than others, and just doing a lot of examples and dealing with the adversity that comes up through using simulation, looking at the root locus plot, getting a feel for what happens when you change the gain, move the zero, is really the way to go forward with it. So let's do an example. So PI control for percent overshoot. So for a plant with the transfer function given, so we've got a plant with 2 poles and no zeros. Design a unity feedback gain controller such that the system has 20% overshoot and 0 steady state error for step inputs. So this is a type 0 system, thinking back to the way that we categorized systems in terms of steady state error performance. A type 0 system, if you go back and look at that table, type 0 system for a step response has finite steady state error. We could compute what that is, but we already know it's going to be finite. We already know that we want 0, so we're going to have to add an integrator in there. We'll use PI compensation. So that's what we'll do. We'll march through our design rules, and we'll see if we can come up with a controller design for it. And I'll just work in Matlab for this example. So I just started a script here. Let's define this system. So we have our plant transfer function. So I'll just do g equals. It's in the form of it has factored out polynomials, so we can read off the zeros and poles from it and the gain. So that's what our method will be in terms of determining, or in terms of defining the system. We could use TF, but then we would have to multiply out this factored out system, so there's no point in doing that. So we'll just use ZPK, and what we need first are the zeros. There are no zeros, right? So empty array. The poles are at -2 and -5, right? And then the gain is 10. So it's good to just evaluate that and see if what it spits out looks like what you're expecting. So that looks right to me. So then I'll put a semicolon at the end of the line so that we don't have to look at that every time. Okay, so we've got our system G defined, our plant, and now we would like to go through and do our proportional controller design, right? So okay, so we can do that based on just the root locus, right? We can just look at the root locus for this system, and we can choose a gain that meets our performance criteria. Our only transient response criterion was that the percent overshoot needs to be 20%, which corresponds to a very specific ray that starts at the origin and goes out into the left half plane, and so that's we're expecting to intersect once or twice maybe with the root locus. So we'll have maybe one or two options in terms of what our gain will be in order to satisfy this. So let's look at what the root locus looks like first. So just like a naive, our locus, we don't know what gains we're interested in yet, so we'll just give it G with no specific gains, and we'll just see what it looks like. So also open a figure. Okay, so we have this root locus. Kind of makes sense, right? We could have sketched that. Two real poles, no zeros, so they're two asymptotes, zeros and infinity. They just go straight upwards at pi over 2 and straight downwards at -pi over 2, and they split the difference. So they come together and then they split off. And we are interested in a specific percent overshoot. So we know if we look at the data cursor, Matlab actually gives us that, right? For different gains, we can see, so a gain of 0.489 gives us a damping of 0.9 and a percent overshoot of 0.115. So that's something that is much too damped for us. We want to have a percent overshoot around 20%. So as we increase the gain, we see that our percent overshoot goes down, but we really need more points here. We want to see, so the gain only went up to 1 here. Let's do it again with the grid on, and let's make sure that we go up to higher gains than this. So let's do grid on, and let's do gains. It's always hard to choose what they are, but something that you can do that's pretty safe is we know where the root locus is in general here. So for small gains, we don't really care about it for those. So let's start off at a gain of let's just do a simple linspace. I did sort just in case we wanted to add in specific gains later, but let's just do a linspace of gains from 1 to say 100, and let's do like 200 gains. Okay, and I think I've got that all correct. So let's try that. Okay, so this gives us the part that we might be more interested in. Let's see at the highest if we're getting close. Okay, so the percent overshoot is 67%, so it's higher than what we're interested in. So let's go down, lower the gain, see, we got percent overshoot of 20. Okay, we passed it. Okay, between a gain of 4.48 and 4.98. Now we could get super precise at this point. We could like put in more gains in between 4.68 and 4.98. Figure out what is the exact one for 20% overshoot. But we're about to F all this up, right? We're about to put in a pole and a zero that are going to change this. So getting super precise at this point is probably not a good use of our time. So let's say we get 20.3% overshoot if we choose a 4.98 gain. Let's just do that. We're gonna retweak our gain after we add in the compensator. So let's just choose a gain of 5 because we're really close to 5. So since we don't need to be super precise at this point. Let's do K1. So I like to name these things as we go along. You could name them like KP and then K. I and then etc. Except that we have a specific definition for what KP, KI, and these things, these other gains are. And when you use cascade compensation, you're putting in an additional gain that's not our definition of KP and KI. So I just call them K1, K2, K3 as I go through and cascade more gains. So K1, let's make 5. And so we have our proportional controller designed. We feel relatively confident because this had no zeros in it. We feel pretty confident that if we simulated this, we would get something with 20% overshoot. But it would be good to check. We'll do the simulation. We'll do the closed loop transfer function. We'll do the simulation, and then we'll add the compensator and we'll do another simulation. So let's do a so before we leave this proportional controller design, we should actually make a closed loop transfer function, right? So let's do G closed loop P. Okay, so this would be closed loop transfer function for proportional controller only, and that gives us, we can use this nice feedback. We're assuming unity feedback. Nothing was described in the problem, so we can just use unity feedback and go forward assuming that. G is the plant, but we just designed a proportional controller, so G1 or K1 times G. So feedback system is just unity feedback, and that gives us our closed loop controller. And now let's do a little simulate and plot. So let's open a figure and let's plot. Well, before we open a figure, let's simulate it. So let's put in a time array, TA. We don't really have an idea on timing yet, like how long something takes. We could do step input just to see like what it does, but let's just guess. I honestly don't know. If I look back at this, we have our real axis. Remember, it's 4 divided by the real axis value in terms of the settling time. That's our settling time estimate, right? So I would say probably like 1 second would make sense. Maybe like 1 to 3 seconds I would simulate first and see what that looks like. So let's do linspace. Let's go from time 0 to like maybe 2 seconds, and we'll do like 100 points. And to do the step response, which is what we're interested in here, let's just do it, let's call it YP, which is for the P controller. What's the step response, closed loop step response? We could do step of our closed loop GCLP, and I think that's all we need. So that should give us our step response. Let's plot our step response here and see what happens. So I'm going to just rerun this whole thing from the start. Oh, doesn't like it. Oh, I didn't tell it in step what my time array was, so it just gave me back YP with some time array. So let's do TA, so it knows what time array we want. And there we go. So I'll put in a grid and we'll rerun it from the top, just to get rid of this red here. I don't like seeing errors, so just prove the error is gone. There we go. Okay, 2 seconds. I honestly didn't go through this right before here, so I don't remember what. So this was just luck. It was a good guess based on some criteria that we had. So 2 seconds was about right. Notice that for a step input, we would like to have, so this is the command going to 1. We would like our response to go to 1, but it does not. It goes to like 0.821, something like that, and we have a steady state error, pretty significant steady state error. We don't love that. Percent overshoot though looks to be about 20%. You know, maybe it's 18%, but in that range. So it looks like our transient response looks good, but our steady state error is not. So that's why we're going to add that integral compensator and see what happens. So we're going to keep wanting to do this simulate. We're going to keep wanting to do this simulate and plot thing. So what I'm going to do is put in the integral compensation section above that, and then we'll include the integral compensator in our simulation and plot. So let's do our Compensator. So with this compensator, remember, we're just going to put a pole at the origin, and then we're going to put a 0 somewhere, and then we're going to adjust the gain. That's really all there is to it. So let's put in a C, so our compensator, it's the integral compensator, so I could call it CI if I wanted to, so CI. The integral compensator is just going to be, and I can make it, I'll just use ZPK, so ZPK, and we want to have a 0 somewhere, so some, like, I said a rough estimate was negative, the real part of the closed loop pole is divided by 10. So if we go back to our root locus, that's like negative 3.5 divided by 10 would be like negative 0.35. So that's like a place to start, right? Yeah. So negative 0.35, and then our pole for an integrator is always at 0, right? And then we'll just have a gain of 1, and we'll adjust the gain separately. So there's our compensator. And first, let's just close the loop and just place that in. So actually, sorry, having a little difficulty here. I will be back. So I'm gonna shut this one down and add another one. So this is part 1. Be back for the, don't miss the end. It's gonna be great. See you in a minute.